So now that you know about what makes inverse functions, we're going to just talk a little bit more in depth, and we're going to start finding the inverse function algebraically. So first off, if I have f of x and I wanted to find the inverse function, okay, I'm not going to call it g of x. The notation for saying the inverse function of f is this, okay? This is not a property of exponent. This is just notation that is used. This means the inverse function of f of x. Now, notice, it says the inverse is also a function. So if the inverse is not a function, you do not use this notation, okay? This notation is is reserved for when it is the inverse of f of x and it's also a function. So remember, being a function means each input has exactly one output. So how do you graphically check whether or not a function is, a graph is a function? Well, you do what's called the vertical line test. Okay, you're checking to make sure that each x only outputs to one y coordinate. So remember, vertical lines are when x stays constant. So your graph should never hit any one vertical line more than once. Okay, so does this pass the vertical line test? Yes, so that means that this is a function. Okay, does this pass the vertical line test? No, because for this one value of x, okay, that's the same x that's giving you two different outputs. So this fails the vertical line test. That means that this is not a function. Okay, this relation is not a function. Okay, so what we want to know is, now, not only do we care about is f of x, okay? Obviously, if it's giving the notation of f of x, it is a function, but we want to know not only is the original equation a function, but is the inverse equation a function? So that's what we're going to talk about right now. Is the inverse a function? Because if you're starting with a function, okay, you're going to want to be able to create, not only find the inverse, but you're going to want to make the inverse a function. So is the inverse a function? Well, let's look at some examples. If we let f of x be 2x plus 1, okay? Just a quick example. So let's say we plug in -2, -1, 1, 2 to help us graph, although I know we know what this looks like, okay? Plug in 0, we get 1. Plug in -1, we get -1. Plug in -2, we get -3. Okay? Plug in 1, we get 3. Plug in 2, we get 5. Okay? So, if you want to know, is the inverse of this a function? Okay? Now think about, the reason I actually put a table here is to help you think about this. Okay? If I wanted to make the inverse and graph the inverse, all I have to do is take each of these coordinate points, okay, for the inverse of the original and flip it. -3, -2, -1, -1, 1, 0, 3, 1, 5, 2. This would be the inverse table of f of x. And if I graph this, -3, -2, -1, -1, 1, 0, okay? Look at that, okay? This was f of x. This was the inverse. Does the inverse of f of x pass the vertical line test? Yes, okay? Now, we didn't actually need to see the inverse in order to know whether or not the inverse was a function, okay? Number 2, if we graph f of x equals x squared minus 1, okay? We do a few points, -2, -1, 0, 1, 2. Plug in 0, we get -1. Plug in 1, we get 0, 0. Okay, 3, 3. Okay, and so that's f of x. x. And now if I said graph the inverse, okay, the inverse of f of x would just be when all of the x's and the y's have swapped, when the input and the output have swapped, okay? So when every coordinate point has flipped, you have an inverse. So that would be 3, -2, 0, -1, -1, 0, 0, 1, and 3, 2, okay? So if I graph this, 3, -2, 0, -1, okay, -1, 0, 0, 1, and 3, 2, does the inverse of f of x pass the vertical line test? No, the inverse is not going to be a function here. Now, we didn't have to actually look at the graph of the inverse to figure that out, okay? You can actually take apart this graph, this table of values of f of x. Now, notice, in our table here, -2, 3, and 2, 3, okay? If two different x's give you the same output, then if you flip the table, that means there's going to be one input that gives you two different outputs, breaking what it means to be a function, okay? So because if I took a horizontal line, okay, and f going through f of x, if I took a horizontal line, okay, and see how two different x's just gave me the same output of 3, that means for the inverse, an input of 3 is going to give me two different outputs, 2 and -2. So there's something called the horizontal line test, okay? So the horizontal line test called HLT, okay? What you do is, it determines whether the inverse of the equation you are testing is a function. Okay, so we'll say, here's a question. Is the inverse of the following relation, we'll just say graphs, a function? Number 1. Okay, so we'll do, let's do this. Actually, I have to make it a little better than that. Okay, so for this function, number 1, okay, we can see we start here and we keep growing up, 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 and we're going up. So if I want to know whether or not the inverse of this would be a function, okay, I would want to take the horizontal line test to this graph. And if there's any place where I would fail, what that means is there any place that would hit, my graph would hit any horizontal line more than once? And the answer to that is no. This passes the horizontal line test. So since it passes the horizontal line test, it means that the inverse is a function. Okay? Number 2. Okay, I've got a quadratic facing down. You apply, if you want to know if the inverse to this is a function, you apply the horizontal line test. Can you find a horizontal line that would fail? Yeah, this horizontal line right here fails. Okay, that graph fails the horizontal line test because there are two different x's that give you the same output. So in terms of the inverse, that means if two different inputs give you the same output and you swap it, that means that one input is going to give you two different outputs. Okay, so this fails the horizontal line test. That means the inverse is not a function. Okay? Now, if we thought about this, what would have to happen with this graph so that it would pass the horizontal line test? Okay? Start thinking about that, because if I need the inverse to this to be a function, we're going to have to do something so that the inverse ends up being a function. And think about, what does this graph need to look like so that that would pass the horizontal line test? Okay? I'm thinking you might have to start taking some part of this u away so that it would actually pass the horizontal line test. Okay, so we have to know how to get an inverse that is a function. Okay, so we have to make sure we are passing the horizontal line test. Okay, so now we're going to start finding inverses algebraically. Okay, but we're going to do a bunch of stuff. Okay, so directions. We're going to graph f of x and its inverse. Okay, that's going to be number one. Number two, we're going to state the domain and range of each. Number three, we're going to find the inverse equation algebraically. And then four, if inverse is not a function, make inverse a function. Okay, so the first one we'll do f of x equals negative 3x plus 1. So, number one says we have to graph f of x and we have to graph its inverse. So to graph f of x, okay, we just make a table of values for f of x. Quick table of values. If you know what this is, what type of function this is, okay, you know how many points you need in order to define that function. So right here, okay, we've got a line. So 2 points, okay, that'll define our line. And 2 points, why don't we just have a few more points so that we can get a good, accurate picture here of what's going on. So we'll plug in negative 1, 0, and 1. Okay? Plug in negative 1, and what do we end up with? 4. Plug in 0, we end up with 1. Plug in 1, and we end up with negative 2. So negative 1, 2, 3, 4. Negative 1, 4. 0, 1. And 1, negative 2. So here's the graph of f of x. If you need to now notice that it doesn't even say get the equation of the inverse. You do not need the inverse equation in order to graph, okay? Because if you have the table of values for f of x, what's true about f of x and the inverse of f of x is that your x's and y's have flipped. So if the point was negative 1, 4, for the inverse, the point is 4, negative 1. If the point on the original was 0, 1, the inverse is 1, 0. If the point on the original was 1, negative 2, okay, this would be negative 2, 1. Now look, this is the graph of f of x, right? Does f of x pass the horizontal line test? Yes. So what does that mean? That means the inverse is a function, okay? The inverse is a function. So 4, negative 1, 1, 0, and negative 2, 1, okay? Remember, they should be a line of reflection. The line of reflection would be y equals x, which, okay, you can kind of see there. It would be reflections over one another. Okay, number 2 says state the domain and range of each. So f of x, okay, and then the inverse. So the domain of f of x is, we can see, spans all the way left, all the way right. Domain is all real numbers, and the range is all real numbers. Okay. domain of the inverse, okay, we can see it covers everything, all real numbers, and the range goes up and down, all real numbers. Now, remember, whatever the domain is, that's the range of the inverse. Whatever the range of f of x is, that's the domain of the inverse. So number 3, now what we have to do is we have to find the equation of the inverse algebraically. Okay, so the first thing that I do is, okay, I replace f of x with just the letter y. Now, based on the definition of being inverses is how you generate the function algebraically. I'm sorry, the equation of the inverse algebraically. Definition of being an inverse means that the x's and the y's, or the inputs and the outputs, have swapped. So what we have to do right now is we have to swap x and y. So x equals negative 3y plus 1. So this is saying whatever was the output is now the input, whatever was the input is now the output. But we never write our equation in terms of x, right? X equals. So right now, okay, this is an equation of the inverse, but we want to isolate y. Okay, so we want to get y by itself. So we take away 1. That gives us x minus 1 equals negative 3y. Divide each term by negative 3. So we get negative 1/3 x plus 1/3 equals y. And we said this is a function, so you want to use function notation here, okay? So we just replace y with function notation, negative 1/3 x plus 1/3. Okay, so this is the inverse equation of f of x. So we would say this is the inverse of f of x, negative 1/3 x plus 1/3. And now part 4 said if the inverse is not a function, make the inverse a function. We don't have to worry about that. The inverse here is a function. Okay, so we'll practice another one. Number 2, we'll call it B. We'll do f of x equals 1/4 x minus 2, okay? Number 1, graph each, so f of x. We'll start by making a table. Okay, notice this is a line, right? So we'll plug in, let's plug in numbers that'll help us here make it easy on ourselves. So negative 4, 0, 4. If we plug in negative 4, we're going to get negative 3. Plug in 0, we get negative 2. Plug in 4, we get negative 1. Okay. So negative 4, negative 3, 0, negative 2, and 4, negative 1. Okay, that's the graph of f of x. Now, if I want to know whether or not the inverse is going to be a function, I take this and I apply the horizontal line test. Would this pass or fail the horizontal line test? This is going to pass the horizontal line test. That means the inverse is a function. So we can use the inverse notation. Now, to graph an inverse, all you have to do is flip the table. So negative 4, negative 3 becomes negative 3, negative 4. 0, negative 2 becomes negative 2, 0. 4, negative 1 becomes negative 1, 4. And this is the inverse graph of f. Okay. Number 2 says state the domain and range of each. So the domain of f of x, okay, domain of f of x, all real numbers. Range, all real numbers. Inverse, okay, whatever the range is, that's the domain. Okay, whatever the domain of f of x is, that's the range of the inverse. Okay. And then number 3, we're going to algebraically get the inverse equation. Now, because we already know that this passes the horizontal line test f of x, we know that we should be using the inverse function notation at the end once we have our equation. So the first thing is replace f of x with y. Okay. Now we actually do the swapping. Okay. Swap x with y. So that gives me x equals 1/4 times y minus 2. Okay, so now we just have to make sure that we isolate y. And then we have our inverse equation. So, get y by itself. So we add 2 to both sides. That gives us x plus 2 equals 1/4 y. Now multiply both sides by 4. And that gives us 4x plus 8 equals y. So this is the inverse equation. So, because we know that this is a function, we use the inverse function notation. And we don't have to worry about number 4 because we know that this is a function. Okay? All right, the next one we'll do C. Let's do f of x equals the square root of x minus 1 plus 2. Okay, so this is a square root function. So the first thing we're going to do is graph the square root function. First point you'd be able to plug in would be the critical value. The critical value here would be 1, 2. And now let's plug in a few more points to help us graph this. So I'll plug in 2. I'll plug in, I'm going to skip a few. That way I can do it without using a calculator here. I'll plug in 5. Okay, and I'll plug in 10. Plug in 2. 2 minus 1 is 1. The square root of 1 is 1. 1 plus 2 gives us 3. Square root of 5 minus 1, it's the square root of 4. Square root of 4 is 2. 2 plus 2 gives us 4. Plug in 10. 10 minus 1 is 9. The square root of 9 is 3. 3 plus 2 gives us 5. Okay, so 8, 9, 10. 1, 2, 3, 4, 5, 8, 9, 10. Let's graph it. Okay. So we got 1, 2. We've got 2, 3. We've got 5, 4. And we've got 10, 5. And it starts here, right? This is a square root. It starts here and it keeps going up and up and up and up and up. So it's never actually horizontal. So does f of x, does this thing pass the horizontal line test? Yes, it does. This thing passes the horizontal line test, okay? Now, what that means is the inverse is a function, okay? But before we graph the inverse, I want us to just look at something, okay? I'm going to write down the domain and range of f of x right now. So this is square root. We can see we have a restricted domain, we have a restricted range. The domain is x is greater than or equal to 1. And the range is y is greater than or equal to 2, okay? So now, when we make our inverse table, we swap, so 2, 1, 3, 2, 4, 5, and 5, 10. Now, what I want you to think about is, the domain of f was that the inputs had to be greater than or equal to 1, which means my outputs have to be greater than or equal to 1 for the inverse. For f, my range was y, or I should really say the output had to be greater than or equal to 2. So for the inverse, the input, which is x, has to be greater than or equal to 2. So if this was the starting point of the original, this is the starting point of the inverse. 2, 1, and then 3, 2, and then 4, 5, and then 5, 10. And so notice, you get half of a u, okay? It's half of a u. You don't make the whole u because you don't have, okay? Think about it. If you're graphing the inverse of f of x, it should be a reflection over the line y equals x. This is a reflection over the line y equals x, okay? So notice how we flipped the domain and the range, okay? What was the domain becomes the range. What was the range becomes the domain, except look, if it was domain is x and range is y, so you have to think about this as input is greater than or equal to 1, so the output is greater than or equal to 1. Some people like to put an x here in terms of the range, but it's not an x, okay? So now, is the inverse a function? Yes, it is. We've already determined that, right? Because f of x passes the horizontal line test. So number 3, in the directions say find the inverse equation. So we had f of x equals the square root of x minus 1 plus 2. Okay, so first thing is write as y equals the square root of x minus 1 plus 2. It's just easier to see it as y instead of f of x. So now we swap x and y. So that gives us x equals the square root of y minus 1 plus 2, and now we isolate y. So we got to take away 2 from both sides. Okay, x minus 2 equals the square root of y minus 1. Square both sides. We're trying to get y by itself, so that's going to give us x minus 2 squared equals y minus 1. Add 1 to both sides, and we get y equals x minus 2 squared plus 1. Now, what is this the equation of? This is the equation of a quadratic, right? But you don't see the full quadratic. Agree? We don't see the full u here in this picture. That's because, and we know that this is a function, right? So we use our function notation. Notice, it's okay. We can keep the quadratic in vertex form. It actually helps us graph. But the reason, okay, yes, this is a quadratic. If I graphed just this, okay, I would see the entire u. But look what we wrote down in part 1. What's the domain on this thing? The domain on this thing is you're actually not allowed to plug all real numbers into the inverse function of f of x. Okay? That's because, remember the definition of inverses is the inputs and the outputs have swapped. So if the range of f of x was that you didn't get outputs that were greater than, you only got outputs that were greater than or equal to 2, what that means for the domain of the inverse is you can't plug in unless it's greater than or equal to 2. So yes, the equation is a quadratic, but you don't get the full quadratic. So you have a domain restriction. And the domain restriction of the quadratic actually comes because your range wasn't all real numbers. Okay, so we don't have to worry about number 4 because the inverse is a function. Okay, so that was C. Now let's do D. Okay, D is a quadratic. Okay, so let's get a few points up here. Let's see. It's in vertex form, so we can name what the vertex is. The vertex is 1, 3. So if we plug in 0, we're going to get 4. So that means if we plug in 2, we're going to get 4. If we plug in 3, we're going to get 7. If we plug in -1, we're going to get 7. Okay. Okay, so -1, 7, 0, 4, 1, 3, 2, 4, and 3, 7. Okay. There's our quadratic. Now, is the inverse going to be a function? So, does this graph pass the horizontal line test? No, this fails the horizontal line test. So as is, okay, the inverse to this, if we don't do anything, the inverse to this will not be a function. So the inverse, okay, we have to flip all these points. So 7, -1, 4, 0, 3, 1, 4, 2, 7, 3. Notice, see how this and this coordinate points, these two different x's gave you the same output, which means for the inverse, 7 will output to 2 different values. That's a problem. So if we sketch this, 7, -1, then we have 4, 0, then we have 3, 1, and then we have 4, 2, and then we have 7, 3, and we go like this, okay? here's the inverse of f of x. Notice there are reflections over the line y equals x, okay? This, obviously now you can see this fails the vertical line test, right? We knew that because this fails the horizontal line test. So let's look, that was one we graphed, okay? Number two, state the domain and the range of each. So f of x, and then the inverse of f of x. So f of x, the domain would be as is, we didn't do anything, right? The domain would be all real numbers, and the range we get is that y has to be greater than or equal to 3. So I want you to think about for a second what the domain and the range of the inverse are going to be. Okay? The domain of the inverse, remember, the inverse is not a function here. The domain is going to be whatever the range was. The range was that the output had to be greater than or equal to 3. So the domain of the inverse is that it has to be greater than or equal to 3. The domain of f of x was that it was all real numbers. Therefore, the range of the inverse is all real numbers. And look, you can see it. The first x value you get is 3, and then everything to the right, and you produce all real numbers. It's just that each x is giving you two different outputs except that little vertex point there. Now, we're going to do a number 3. Okay, it says that we need to algebraically get the inverse. So the first thing we do is we replace f of x with y. So that's going to give us x minus 1 squared plus 3. Okay, so I'm going to subtract first. Whoops. We swap x and y, right? So that's going to give us x equals y minus 1 squared plus 3. Now we subtract 3 from both sides. Now, remember, we're solving and we're taking the square root of an unknown squared, okay? We just took the square root of y minus 1 squared, which means what we produce is plus or minus the square root of x minus 3, okay? This plus or minus here, this, if you look at this u, okay? This part of the u is the square root of x minus 3 plus 1, and this part of the u is negative square root of x minus 3 plus 1. And when you have both of them, that's what's giving you the sideways u. So the inverse of a quadratic is a square root, okay? But it's actually the plus or minus of the square root, and the inverse, if you don't do anything to just f of x, notice the inverse is not a function. So now we add 1 to both sides and we get y equals plus or minus the square root of x minus 3 plus 1. And you don't want to, for number 3, you don't want to use inverse function notation because this is not a function. Now look, you can see, if I plug in 4, if I plug in the x value of 4, I'm going to get two different outputs because I'm going to have to evaluate this, and then I'm going to have to evaluate this. Okay, so this would not be a function. And now number 4 says, well, we want to make these, well, I should say we want to make sure that the inverse is a function, okay? So number 4, we want to make sure that the inverse is a function. So let's think about what we have to do so that that happens, okay? So I'm going to erase, I'm going to keep what I need here, okay? I need f of x. Right now, okay? And when we had, I need to write down, we had that the inverse equation was y equals plus or minus the square root of x minus 3 plus 1. Okay. So, for number 4, okay, let's think about this. The inverse is not a function because this fails the horizontal line test. So the first thing is we would want this to pass the horizontal line test. So if this was going to pass the horizontal line test, well, I fail because I have two different inputs giving me the same output, okay? Now, if I start taking away part of this u, I'm going to start failing the horizontal line test less and less and less. And I'm going to fail it less and 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 less, and now I passed the horizontal line test. So I'm just going to put in dashed what I just took away. Now Notice, everything I took away, okay, I did not take away any piece of this graph, okay, that takes away from the range of what's left. Everything I took away has a matching pair. Notice, I didn't take away any of the range, right? The range was that y is greater than or equal to 3. You have to make sure that you do not take away the range, any part of the range at all. But what I'm doing is, I'm restricting, okay, what you do is, I'm restricting the domain of f of x. If I restrict the domain of f of x, okay, what's going to happen is, it's going to make this graph pass the horizontal line test, which is going to make the inverse be a function. And that's because I will be restricting the range. So instead of being able to get the entire u going like this, you're only going to get half of it. And does this pass the vertical line test? Yes, it does. So we have to restrict the domain of f of x. So notice, you need to know what the vertex is. The vertex here is 1, 3. Okay? So notice, what we want for f of x, okay, we don't want the domain to be all real numbers. We want either from the vertex to the right branch of the u, or we want the left branch of the u. So our domain is going to be x is greater than or equal to 1. And the range has not changed. It's y is greater than or equal to 3. So now what this means is, the inverse, now that this passes the horizontal line test, that means that the inverse is a function. And that the domain would just be what the range was. The range was that the output was greater than or equal to 3. So my range here is going to be x is greater than or equal to 3. But now look, my domain is not all real numbers anymore. Okay? So my output here isn't going to be all real numbers. It's going to be y is greater than or equal to 1. So if I go back to my original drawing here, if this wasn't allowed, let's see, going by my new domain, if this wasn't allowed in my domain, and this wasn't allowed in my domain, then I should have never had this point, and I should have never had this point. So, my graph, 4, 2, 7, 3, now look at my inverse because I restricted the domain of f of x. Does this pass the vertical line test? Yes, it does. Okay? Now, in terms of the equation, the inverse, what we had right now for the inverse was this. This is not a function. But if you say that you can only have outputs where y is greater than or equal to 1, notice how half of the u went away. Which part of the u, half of the u went away? The part above the vertex or below? Below, right? The values descending from the output value of 1 is now gone. How would that happen? Well, if that wasn't there anymore, okay, now you're only getting the top half of the sideways u. So if you pick to get rid of the left-hand side here, okay, and you keep the right-hand side, notice you're getting just all of the values above the y-coordinate here, okay, which means you would be taking away the minus sign. If you got everything, if you kept everything below and you erased what's on top, you would get rid of the positive sign and you would keep the negative sign there. So notice, we have a new domain and range, okay? We have a new domain for the original, we have a new range for the inverse, and now the inverse function, okay, just looks a little different because we just want to show that we have to have a range where the outputs can't be greater than or equal to 1, okay? Right here, it's saying it could be positive above 1 or below 1 because we have the plus or minus here. Okay, so let's practice again. And we'll make another video and practice one more.